The session starting now is called Next Generation Modeling, which is, I think, might be bad news for people like me who are still trying to catch up to last generation. And this is the last session of the day. This is good news also for you people who have flown all night or all day to get here. Reminds me of when Shukla travels quite a bit. And I once went on a trip with him. It was like an overnight trip, one-day trip to Max Planck Institute to visit Leonard. And we got there, and without any rest, I think we went over to Leonard's house, and Leonard and Shukla talked all day, and then it got dark. And darker, and nobody bothered to turn on the lights, and they kept talking. And I was totally exhausted, but Shukla and Leonard kept at it. So, okay, the first speaker this session, and I thought I'd say a little more about the speakers because I did a poll of the students who are here, and I said, do you know any of these people? And they said, what? What they do or where they're from or anything. So the first speaker is Dame Julia Slingo, OBE, DBE. I think those letters are some kind of advanced medical degree. She's the chief scientist at the UK Met Office and professor of meteorology at the University of Reading, and she's worked at the Met Office for most of her career, but also at the ECMWF and at NCAR for a year. And she spent some time on the COLA Scientific Advisory Committee. So Julia's going to speak on from global to local and from weather and climate to environmental risks and impacts.
Thanks very much for the introduction. Actually, I spent the bulk of my career with Brian at Reading, really, and got winkled back into the Met Office 6 years ago to be their chief scientist.
I knew I'd say something wrong.
But that's fine. And so I still considered myself to be really an academic, actually, but it's been a great privilege to be able to be chief scientist of the Met Office and shape our science so that we're really useful and can do things that the world needs of us. I should also say that, yes, I do have an OBE, and when I got it means you're an officer of the Order of the British Empire, but as soon as I got it, my brother rang me up and said, of course, it stands for Other Buggers' Efforts, excuse the language. So likewise with being Dame, there's nothing like a Dame, apparently. And again, I see that very much as an endorsement of our science, actually, and in particular what the Met Office in the UK does for weather and climate science. So it was a great privilege to be invited by Jim to come and speak at Shukla's 70th birthday symposium, and I consider myself to have had quite a very long and happy association with COLA over many, many years, culminating on being on your scientific advisory committee, which I greatly enjoyed, but also Shukla and I spent quite a lot of time on and off in Trieste, as I remember, at the ICTP, working on monsoon things and working on, I think, something that's also been close to my heart is to help developing world scientists get to know what's at the cutting edge of our science so that they can contribute and take it home and continue to grow science in their own country. And of course, I was thinking back to the World Climate Modelling Summit, which 2008, and prior to that, a meeting in late 2007, a Sloan meeting in central London, which Shukla organised, where I think we really had a visionary look at next generation modelling. And actually, I think quite a lot of it we've sort of made a lot of progress on. And what I hope you'll take away from the talk today is that actually, if I was a young scientist starting out today, boy, what opportunities there are. I think there are going to be some massive breakthroughs in the next decade or so in the way that we can model not just the weather and the climate, but the environment, and how we can use these models to unlock really new understanding about how the atmosphere, the oceans, the land surface work together to create the environment which we live in. And so what I want to do in the next 15 minutes is really literally give you a high-level view of the thinking that I've gone through while I've been Chief Scientist at the Met Office, and I think it resonates a lot with some of the things we've already heard today. So last autumn, I went to a conference in Darmstadt on Earth observation, and I was asked to give the talk at the end of what I thought of my vision for the next 10 years about what Earth observation could tell us. And I came to think the opinion that actually there are two big unanswered questions that are fundamental to what we do. And the first of all is, where the hell does all the heat go? Now that's the reason I said that question, asked that question, was of course the pause in global warming that we've seen over the last decade and a bit has turned everything upside down. We're being challenged as never before on our science. We're being challenged as never before on how good our models are or not. And the reason that we as scientists have not been, I think, been able to give a definitive answer to the pause is because, quite frankly, we still don't know where all the heat goes. And this is just a picture from a nice paper by England et al. Looking at the decadal trends in the Pacific, both at the surface and subsurface. It's just an example that actually there are things going on in the deep ocean that we still do not understand. We, of course, have great difficulty observing them, and our models are certainly not adequate. And they're all about how the ocean atmosphere system works and how heat gets moved down to depth, moved around in the ocean system as a function of ocean density. So salinity comes in there somewhere and re-emerges somewhere at some time in ways that we don't yet understand. So where does all the heat go? And the second one was, where does all the fresh water go? And I think if we look at our models, what are the big issues? It's still around precipitation. We still have major biases in our models of just the mean precipitation, let alone its variability, particularly in the tropics. And this is just a gratuitous picture, but it's the current drought in California. So where has all the fresh water gone? What's driven that big drought in California? Something's going on in the tropical West Pacific that I think some of us don't understand. Why does the tropical Pacific, West Pacific, stay so warm, and yet El Niño's been doing its damnedest to break through but can't quite make it? And is this just the ocean doing its thing, or is it climate change, as Tim suggested, after our severe winter? We don't know. So these are some pretty big questions. And of course, fundamentally, both of those require you to know about circulation. And what really, I think, surprised me in Darmstadt was that a couple of colleagues stood up and said, you know what, for climate change, the big elephant in the room is dynamics. And I thought, well, it's always been dynamics, hasn't it? Climate is about dynamics. And at what point did we go from talking about general circulation models to global climate models? I'm not sure. But I think in that change, we lost a lot. I was brought up on general circulation models, and therefore fundamentally dynamics. And somewhere along the line, we went to global climate models and got caught up in thermodynamics. I'm being deliberately provocative. But the point is that dynamics is everything. And if you want to know where the heat goes in the ocean, you're going to have to be able to represent western boundary currents and eddies and the fronts in the ocean. And we've already seen these sorts of pictures from Ben. An IPCC type model at 1 degree just doesn't do it. We need to be down at least at 1/4 degree. I think that we can see the step change in going to 1/4 degree. For many of us, that's now our working horse model. but we probably need to be down at 1/10 of a degree if we want to understand where the heat goes. And it's not just horizontal resolution, we need to have good vertical resolution. We forget that in the ocean. The ocean boundary layer, the mixed layer, is very complex. There are lots of things going on. And yet, what do we have? 10-meter deep layers in the top of the ocean. We should be down at 1 meter at least if we're going to understand how heat gets moved between the ocean and the atmosphere. And of course, for the atmospheric model resolution, we should all know this because many of us have been exposed to weather forecasting, and we kind of know that weather systems are the rain-bearing systems, and the weather systems and their associated winds transport very important things, in this case specific humidity. And we're now at 60 kilometres, a lot better than our 130 kilometre model, but we should be down at somewhere around what we're currently running our global NWP to have a chance of talking about where does all the fresh water go. So fundamentally, here we are, and I think one of the things I've always agreed with Shukla on is that ultimately, if you're going to make predictions and seasonal predictions and climate change, resolution, improving models is absolutely critical, and that resolution has to be at the heart of it, and it's expensive, and we have to fight for it. And we need to know where all the heat goes and where does all the fresh water go. And as we move into ever more complex models, I've been very clear at the Met Office as we build our next generation Earth system model that they have to start with the best possible description of the physical climate system, because you can't do Earth system modeling if you don't know where the heat goes and you don't know where the fresh water goes. So this is again where I think we need to make sure that longer term climate change, Earth system feedbacks, Earth system models, that we have a strong voice in emphasising that point. So that's a bit of me as a scientist saying where I think next generation modelling has to be. Of course, I've been deeply affected by being the chief scientist at the Met Office. Oh, sorry, I've got one more thing to say. I was going to move on to the next. And of course, fundamental to all of this is convection. And so we have, as a community, got to sort this out. And I don't believe that just ad hoc playing around with parameterizations is going to be the solution. The fact is that with increased computer power and the way in which we're able now in weather forecasting to run routinely at kilometre scale, I think has opened up a whole new era of what we can do around parameterization. And this is coming back to one of my other key drivers of all the research I've ever done, is that our models are laboratory. And we at last have some laboratories with these kilometre scale and sub-kilometre scale models to actually really get to the guts of how does convection interact with the local dynamics and organise itself. We've had hints of that through this morning's talks. And this is just a slide showing actually some work we did in a project called Cascade here, where which I started up when I was at Reading University, where we were using kilometre scale large domain models to try and understand what convection was doing. And this is just an example of a very beautiful but actually incredibly realistic simulation of a real typhoon, Typhoon Meggy, by a 1.5 kilometre model showing amazing structures and so forth. And we have to learn to use these and in a way extract from them what are the fundamentals of what convection as a thermodynamic and dynamic process is doing. And this is a lovely quote from Doug Parker at Leeds. He says, "We've broken the sound barrier." And I think he's right that we're now entering a golden age where we can actually really get down to looking at the fundamental physics, the processes that go on in these important things like convection, and of course its interaction with the boundary layer and with the larger scale flow, and really maybe think of different paradigms for how we do convection. And this has been expressed in a new programme in the UK. We've worked here with the Research Council, and together we've committed £10 million for the next 5 years on a major programme with the academic community. This is our academic partnership, and with the Research Council, to really exercise these kilometre scale and finer scale models to see what we can get out of them in terms of describing a new parametrization scheme. It's my belief, and I think however you cut it, we're not going to be able to do global modelling at a kilometre scale, at least for the next decade, for all the applications we have. So this is badly needed. And I think we'll learn some amazing things as well. And we're hoping that other groups will participate in this programme. I think there's enormous value for other groups that are engaging in kilometre scale modelling and Earth observation to really join together and see what we can understand about convection. All of this means big computers. And one of the big challenges we have, I think, in the next 5 to 10 years is to transform our codes to work on very different computing architectures. We're going to hear, I think, a bit more about this from Jim, and I know Tim's going to touch on this. This is a big change for us. We've spent 40 years roughly doing it the way we've always done it. That won't cut it, I don't think. And we've had this programme running now for nearly 4 years in the UK, looking at what sort of grids, what sort of numerical algorithms we need to be able to work on massively parallel machines. And again, really good opportunities for collaboration. I don't think there'll be a single solution, but it's really interesting to compare different solutions. Of course, where I come from this is that it's not just about building the next generation model, it's also about building the next generation forecasting system. So there are some things, for example, the use of more exotic adaptive grids that are probably not a goer if you're looking at what your operational system is going to be like in 5 to 10 years' time. And that has very much, I think, flavoured also my views compared with what they were, say, at the Sloan workshop in 2007 and the modelling summit, that actually, at the end of the day, it's about making forecasts, it's about making predictions, and those things have to be made within a certain time window, and they have to be robust, and we have to be able to deliver information on time. And you have to then say, well, what does society need of us? And that very much then, for me, shapes what I think our next generation modelling should look like. So if I was asked, well, what are the 5 drivers for Met Office science, then they're these here, and at the top of them, of course, it's about saving lives and livelihoods. And I was just talking to Lou, and there's a lot of common thinking, I think, between where he's going with the National Weather Service here and where the Met Office is going. And of course, you can go down and look at all of these to do with adaptation, climate change, and as you'll see as the talk progresses, that what we need to save lives and livelihoods today is the same sort of things that in many respects we need to talk about wise adaptation in the future. We're very lucky, I think, at the Met Office because quite a long time ago, Mike Cullen and colleagues made the decision that we would have a unified model with a non-hydrostatic core. And I remember when that came in, and it caused a lot of angst in the climate part of the Hadley Centre because the non-hydrostatic core was pretty expensive. But actually today, I'm enormously grateful for the people who stayed there and stuck with it and kept the non-hydrostatic core because it's allowed us to run a truly unified system across all time scales and across all space scales. And although the unified model formulation, or the bells and whistles, should I say, of the unified model are different depending on which time scale you're looking in your forecast lead time, the guts of the model is common. So a lot of the things about the model are same across all time scales. So we run a seamless prediction system from hours to decades. It will be, by 2017 or 18, fully coupled across all timescales from days to decades. But as I say, it changes as you go out, and this becomes, of course, much more an Earth system model than a physical weather and climate model. But equally, deeply embedded in the way we think is this idea of from global to local, that ultimately, however you look at the weather and climate problem, what you need to know about is what it means to me and where I live. And that means being able to say what's the probability of a local hazard and what would be the impact of that local hazard on me as an individual, on where I live, on where I work, and so on and so forth. And we've had this in our strategy since I came to the office, that this is what we would drive towards over the next few years, of getting our global model for climate and weather down at what I call the synoptic resolving scale, 10 kilometres. We would use that to drive a regional downscaler, dynamical downscaler, if you like, at 1 kilometre or less for the local meteorology, and they would interpret the outputs of that in terms of what our customers require. And it seems to be a good strategy and very good use of the computing resources that we currently have available to us. So here's just an example of the sorts of things now, the sorts of capabilities that we have. This is our operational kilometre scale model running in a situation with, as you can see, a front low pressure system pass across the country. Here's the model, here's the radar. If you looked at these two, you'd say, well, it's pretty good. But actually exactly where the most intense rainfall is quite different. It's the flap of the seagull's wings. It's chaos at the convective scale. And so we don't run just one forecast, even just for a few hours ahead. We run an ensemble. And so what the forecaster gets now is a probability of the chance of heavy rainfall in the hour, so that they can see where they need to issue their weather warnings. And we wouldn't be able to do this sort of thing with that level of detail if we weren't down at this sort of kilometre scale. It's been a revolution, I think, in weather forecasting, and a revolution in assessing risk, the whole use of ensembles at the convective scale. There's a lot of science still to be done. But of course, it doesn't have to apply just to weather forecasting. We've also applied this to climate change, and I think this has been one of the most exciting papers on climate impacts for quite a while. This was published in Nature last year. It's the first attempt to say, if you could do kilometre scale modelling for climate change, what would it tell you about something as important as flash flooding? This is a big deal in the UK, particularly in summer. And what we were able to show by using our 1.5 kilometre model in climate mode, so this is running it for 20 years, computationally at the edge, so it's only for the southern half of the UK. We run it for the current climate. It verified very well against statistics from the radar system. So we know it does the intensity, frequency, characteristics of rainfall well. What does it say if you apply it to the end of century climate change against what would be a standard sort of IPCC downscaling regional climate model? And what we can see is that whilst in winter, the difference is not that great, and it's pretty close, so this is the top 5% of hourly rainfall, pretty close to Classius-Clapeyron. What you can see in summer is, in fact, that the 1.5 kilometre model is looking at much more intense hourly rainfall under climate change. So this is what we've been beginning to sort of but see in observations, that in some situations there's a super Classius-Clapeyron behaviour where the dynamics adds to the thermodynamic response to climate change and leads to extremely heavy hourly rainfall. And if you were in the business of designing your flash flooding drain system, you'd probably want to know that this was perhaps a possible outcome, rather than what you might have got from a very standard climate resolution regional model. So this is really opening up this seamless nature of looking at the impacts of climate change at the local level, using all the science and modelling techniques that we have at our disposal for forecasting the weather. And we can go further than that, and I think the subject is going further than that, and this is, for me, really exciting because, as I say, it opens up a whole new way of looking at some fundamental physical processes. This is fog at Heathrow in a 300-metre model. Here it is in our standard 1.5 kilometre model. That's the landscape of the Thames Valley in that model. This is the landscape of the Thames Valley in a 300-metre model. And all the little valleys, the reservoirs that exist around Heathrow are there. And we get some very, very interesting and potentially very useful fog forcing coming out of a model at this sort of scale. So at the guts of this, of course, is understanding the processes that go on in the boundary layer and in the cloud top boundary layer, and in how fog forms in the boundary layer, all of which is new understanding of physics. Another example here from the Olympics. This is when we were doing the sailing event in Weymouth Bay, and this was, again, a 330-metre atmosphere driving a 250-metre wave model. The sailing fraternity at the Olympics said these was the best forecasting they'd ever had. The reason I show this is that this is beginning to look at some really interesting things to do with not just the winds, but the winds and the waves together and their impact on the coastal environment. And this is not a trivial point. That was a sailing event. Here's the Thames Barrier. And last year, this is the history of the closures of the Thames Barrier since it was built in the 80s. This is last year, and it was closed over 40 times in the winter of 2014. Not just because of storm surge up the estuary from the North Sea, which it was built to protect London from, but also fluvial flooding, the volume of water coming down the Thames from the very severe rainfall we had. So it was tested very severely. And I think if we're really going to be able to do assessments of the whether the Thames Barrier is fit for purpose for the next few decades, we're going to have to think about the full coastal environment. So that's led us to develop a new programme, and this is really next generation modelling towards a UK coupled environment model, where indeed we don't have just the atmosphere that I've been showing you. We couple it to an ocean, we couple it to a land surface with full hydrology and river flows. We couple it to waves and ultimately, of course, to sediments and the biogeochemistry. We started this project about a year and a half ago in collaboration with the Natural Environment Research Council, and it's going really well. This is the domain of the 1.5 kilometre scale ocean model that is being coupled to the atmosphere. That's the grid around Western Scotland. You can see the quality that the ocean, the shelf seas model will have. This is the difference in the coastal wave model. This is for a very high wave event in the early January in 2014. And we can see the difference from a low resolution model to a high resolution and the sort of waves that will impinge on the coastline. Here's the kilometre scale ocean model and the tides that are in the model, and therefore the sea surface height around the British Isles, which is crucial if you're going to talk about storm surge. It'll be the combination of the tides, the winds, the waves, the bathymetry of the coastline, and everything like that. So this is opening up a whole new vista of what we can do in terms of environmental forecasting and not just weather forecasting. And if we think about climate change, this is the sort of thing we need to talk about in the future for climate change. It won't be about just what the weather does. It'll be what does it mean for the environment in which we live. So here's a good example of why we would want to build this. This is the UK just over a year ago. Massive waves, huge flooding of the Somerset levels, the railway line just west of Exeter severed for weeks and weeks and weeks, very difficult to get out. And we need to be able to say, if this is the sort of weather we're going to have, what are the impacts going to be? So one of the other things we need to start thinking about is how we take the information on the weather, and in this case, the waves and the rivers, through into what the user requires. And that means thinking about what we do in the context of a much more complex set of issues to do with the exposure and vulnerability of the customer, whoever that may be, what the socioeconomic impact will be, and therefore how do we quantify and reduce risk. And that's going to, I think, modify a lot the way, the priorities that we put on where we place our effort in terms of the science and the modelling and how we exploit the computing resources we have in the coming years. So just finally, here's just a little noddy example of the sorts of things that one can start to do. And this is, again, an old example, very strong winds across the UK here on the 3rd of January in 2012. This is the wind gust speed in the morning. Well, you could have issued a forecast for high wind speed, but actually what was far more important was where that was going to happen, how many lorries were likely to be on the roads, at what wind speeds are lorries overturned, and therefore where do you start closing bridges and expecting disruption on your major road network. Here's the road network for the UK. It's now coloured in that red, yellow, green warning system so that the Highways Agency know where there is going to be high risk and where maybe they'll have to close bridges and so forth. It's very effective. But it is actually now interpreting the weather in terms of an impact. And this is all the sorts of things that Lou was talking about earlier this afternoon. This is, I think, has to shape the way in which we develop our future modelling. So some key challenges for the future from my perspective, preparing for future computing architectures. Jim will touch on that a bit later. We've known that's been going to be a big deal from when we were meeting in 2007 in London. We really need to drive down model resolution at both the global and the local scale, and in the horizontal and in the vertical. I think we need to gradually move our science from weather and climate to the local environment and global Earth system. One thing we have talked very little about this week is the observational base, but that has to be now become a really key part of our strategy as modelers, because if we don't keep the observations in pace with the model development and the resolution of the models, we are in danger of living in what I call fairyland. Everything has to be rooted in observations. So this is a big challenge for us, and we need to make sure we've balanced our investment appropriately. And then effective translation and application of weather and climate science from hazard to impact. And of course, always, and something that I've been very keen on since I came to the Met Office is working in partnership. That these things are far too big for one organisation to do. International cooperation has always been so important for us as meteorologists, but never so important, I think, now, when we have to share data, knowledge and capabilities and the sort of resources, big science, big data, big models, big computers, to do what we need to do. So one of the things I think Kola and Shukla, you've always been very good at is encouraging international cooperation, right from the early times that I got to know you and seasonal forecasting and so forth. We need to do that more and more and realise where our individual strengths lie and how we can bring them together to best effect for the future. So thank you very much. I'll just leave that running. This was something that Kamal Puri gave me last week when I was with him in Singapore, and it's actually the Australian simulation, again, with the unified model which they now use in partnership with us. And it's just a great example of capability that they now have. This is an example of the wind speed at 10 metres from a 400-metre simulation of the wildfire event that happened on Ash Wednesday in 1983. And it just gives you a window into the sort of immense capabilities that we have now at our fingertips to understand all sorts of things about how the atmosphere works.
That particular example I was there, Ash Wednesday.
Yeah.
And you'll see the cold front
In a minute.
through. It's coming through now.
There it is.
And it came through, I think, a tiny bit early, and a whole heap of fighters were killed.
Yes.
So that the question I had though is communication. The more information you develop, Lou was talking about how difficult it was to communicate a storm surge, but now with so much information,
yes.
I normally think of developing world issues, but even in the United Kingdom, advanced and all, it would seem to me the enormous amount of data communicating almost on a street-to-street basis must be a challenge for you.
Yeah. Well, we do a massive amount in social media, actually, huge amount, and through apps. We have to embrace, actually, 21st century communication. Social media, amazingly effective. We can reach, when we need to, tens of millions of people through social media by just having the right people who will push it on to their folk. So I think the 21st technology is going to be a really big deal in this, and we need to think about how we do that most effectively and how the message is communicated.
So first, I wanted to thank you for your very inspiring presentation. It was fantastic. In one of your earlier slides, you mentioned the need to focus prediction on societal impacts and risks. And towards the end of the presentation, one of the slides showed the future in the UK coupling of different models of ecosystems and water and climate and weather. So when do you envision that there would be integration of the human system and the social system into this suite of models?
Right. Well, Eugenio sort of raised this earlier on, actually, and gosh, I don't know, and I think that the point is whether you want to do it as a two-way interactive system or a one-way interactive system. The one-way thing is much more tractable. In other words, what's really important in the work that I'm now engaged with in the Met Office is dialogue with the customer, whoever it is. Absolutely understanding their needs and therefore how they can fit into this system, and we can give them what they want. That's a sort of one way, if you sense, here's the forecast and we'll package it up for you in that way. The sorts of things that Eugenio was alluding to, which I think I remember we talked about at the Sloan meeting, was this idea of humans being an integral part of the Earth system for longer term change, and how human behaviour will interact with what happens to the Earth system as we go through climate change. And the integrated assessment models try and do that, but they do it in my view, a very simplistic way. I think we're a long way from really having a clear view on that, but I think it's really important that we begin to recognise that there is potentially a two-way interaction between how the Earth system evolves and what humans do, that actually will be very complex and probably very non-linear, and will change the outcome very dramatically. And I have no idea when we'll get to that point. But just recognising it is really important.
Okay, thank you, Julia.